Okay, so a couple things before we get started. A couple small changes, minor changes for this semester. Something, this doesn't really apply to you guys so much. I don't think it'll affect you hardly at all. But I'm going to do it for my other classes, so I'm going to do it with you too. I'm going to not leave tests open forever. I'm going to give you a period of time to wrap them up, and then we're going to close them down. So probably 2 weeks. Right? So there'll be when we take a test, I'll leave a period, an interval open where you can go back and you can do some retests. Now, I'll give you multiple reattempts on it, but then I want to close them down. I want to close down the homework and the tests for that section. I'll just program them in Moodle so that there'll be a due date that'll show up on the calendars. It'll tell you when things close for good, and then when they close, what it'll do is it'll just auto-submit. If you've got still an open attempt, it'll just submit it for you, and that's the score you get. So just be aware of that. Check the calendars. It's not a big deal. I don't think it hardly ever would come into play with you guys, but just so you're aware, one little change I'm going to make. I want to encourage you, if you're not using the notebooks as much as you should be, I got kind of lazy with that, do that. That's important. I mean, make sure that when you're asking me a question, I'd like you to have, if it's a problem where there's nothing to write down, then that's understandable. But if there is something that you could be writing down, write it down. Okay. Even it's not as big a deal in geometry maybe as it is in algebra, but in some cases it really is handy to be able to draw a picture and fill in geometric information as you encounter things and you figure things out, and you uncover congruences, mark the drawing up so you can see all that stuff. Okay, what I want to do today, we've covered 5.1. We just went through 5.1, didn't we? Yeah. I'm gonna skip around. I think I mentioned this to you. There's some really cool stuff in chapter 5 that I want to come back to, but I'm gonna skip it for a while. We're just gonna hit the highlights of chapter 5. And then it won't take long. We're only going to cover, I think, 3 or 4 sections in chapter 5, and that'll be it. This is one of them. We talked about perpendicular or bisectors, perpendicular bisectors of segments last time, I think, right? Now we're going to look at the midsegment theorem. Not heavy-duty stuff at all. Pretty minor league stuff, really. But there's some important relationships. So, midsegments of a triangle, I want you to understand what a midsegment of a triangle is and be able to use the properties of midsegments to do stuff, to solve problems related to a triangle. So, we haven't really done this. This assumes that we went through 5.2 and 5.3. This is some of the stuff that we'll come back and hit later. Angle bisectors, medians and altitudes. I'll give you definitions for those. In fact, I'm going to do that right now. I want you to know what these things are, but we're not going to do anything with them for now. So if we have a triangle, let's say we got a triangle like this. Okay, what is an altitude? Let me label these. What's an altitude? Did you talk about that in middle school at all? Okay, an altitude is what you get if you, and this is the language that a mathematician would use, if you drop down an altitude from one vertex perpendicular to the opposite side. So if I wanted, there are 3 altitudes that we could draw. Here's one of them. One of them is right there. Okay? Because it's perpendicular to side AB and it passes through vertex C. Right? So we would call that dropping an altitude down at point C, or vertex C. Okay? What would the altitude look like if I dropped it down from point B? Yeah, it's gonna intersect A and C perpendicularly, so something kind of like that. Does that make sense? Okay, I just want to show you something kind of cool, and we'll come back and talk more about this later. This is kind of interesting. What if I drop down an altitude from vertex A? Going to meet on C and B somewhere. And is it a coincidence that they all meet at one place? No. It's not. That's one of 4 different kinds of centers you can define for a triangle. And that's what we'll come back at the end of the year and talk about, the different kinds of centers and what they mean. They actually have some meaning in physics with these different kinds of centers. And so anyway, but the important thing I want you to know here is the definition of the word altitude. An altitude is just a segment that connects one vertex to the opposite side perpendicularly. How would I do it for a triangle, like an obtuse triangle like this, do you suppose? It'd be easy to drop altitudes down from, well, from B, it'd be easy. How would I drop an altitude down from C, though? Yeah, I'm just going to, if I drop a line down from C, or a segment down from C, perpendicular to AB, it's going to miss AB, isn't it? Right? That's okay, though. All we do is we just extend side AB, like so, and this becomes our altitude. Okay. And funny enough, it still works. If we still cross all of the altitudes, watch what happens. If I continue that, if I make an altitude now that goes from A down to its, intersects the opposite side perpendicularly, what's that going to look like? Well, I got to do this, don't I? All right, so I get something like that. If I continue that, they intersect clear down here. Well, what do you suppose happens if I drop an altitude down from B? There it is, right? But if I continue that altitude, if I extend it, look what happens. They still cross at the same place. It's pretty bizarre. Okay. If we talk about the length of an altitude, though, because a lot of times, and we'll see this at the end of the year when we talk about formulas for calculating like volumes and areas and surface areas and things like that. The length of an altitude is just going to be that part of the segment right there, right? It's the distance between the vertex and the opposite side or its extension, right? That makes sense. So I guess what I'm saying is, if I draw this extension of the altitude, well, that's okay to do, but this part right here is still, the green part is the length of the altitude. Okay. Just wanted to give you a heads up about that. We'll come back and talk about that later. It's not a big deal. You know, we'll come back at the end of the year and hit some of this stuff a little bit more. Okay, for now though, midsegment. So a midsegment of a triangle is a segment that connects the midpoints of two sides of a triangle. So something like, come on, like that. Okay. So if I've got this triangle and I calculate, I find the midpoints and I connect them. Let's just play a little bit here, and we're going to mess around with this on Geometer Sketchpad. See what we get. See if we can uncover some properties of a mid-segment of a triangle. So let's draw a triangle, how about? There's my triangle. I can tweak this triangle if I want to, and all the stuff that I do to it will respond accordingly. So let's calculate a midsegment. Let's go ahead and find the midpoint of this side, which I can do in Sketchpad pretty easily. I can just go up to, if I highlight the side and I go up to construct, I can construct a midpoint. Right? Let's do the same thing right here. And I'm going to label all these so we can, how do I do that? Display, show labels, there we go. Oh. How do I do that? I don't want to label everything, it turns out. Just want to label some things. Okay, so what segment is going to represent the mid-segment of this, a mid-segment of this triangle then? DE, right? want to hypothesize here. You think there are going to be some relationships that are going to pop out. Elton, what's one? Give me one thing.
If you draw a mid-segment, the triangle created by the mid-segment is similar to the whole triangle.
That's true. And we'll get to that. When we talk about similarity, we'll get there. Okay, what about something else? Something a little less complex. Yes, ma'am.
C would now be parallel to AC.
Ah, okay, let's check that. It looks like they'd be parallel, doesn't it? Let's check that. So we can do that too. Let's go ahead and calculate a slope. Measure the slope. Oops, I don't want to do that. It always does that for some reason. Height grid. There we go. Oh, okay, so the slope, that's pretty small, but the slope of segment DE is 0.4282. What do you know? The slope of, they labeled this as line L for some reason, but so it's got a label there. But it means that bottom side of the triangle. They're equal. And what's more, if I tweak the triangle, they stay equal, right? So that must be a general relationship then, right? So the slope of the mid-segment of a triangle is always parallel to the side. I don't want to. What do they say there? It's going to be parallel to. Well, yeah. How do they say it in the book? I can't even remember how they say it in the book. We'll come back to this. There's specific terminology that they use. And I can't remember what it is.
Isn't it the side that's not?
Yeah, it's the third side, they say. Okay, the segment connecting the midpoints of two sides of a triangle is parallel to the third side, okay, or the other side. Okay, does that make sense? So, whoops. Okay, so for us, the mid-segment is formed by the midpoints of sides AB and BC, and so it must be parallel to side AC, right? Any other proposals here? See anything else that might be a relationship? No, what do you think?
It's perpendicular to side BC.
Perpendicular to side BC. It looks like it, doesn't it? Does it still look like it? No? So that one, good idea. That one didn't pan out. Have you got any other suggestions? What do you think? Yes, ma'am?
BE congruent to BC.
Yeah, it definitely is. And we know that's true. That's a midpoint, right? So we know that has to be true also. That's something we sort of already knew. Is there something specific to this situation here where we've got this big triangle that's being divided up by that mid-segment? What do you think?
Angles of BDE equals BAC.
Yeah, that's true. That's true also. And that's something that I would claim that maybe we already knew also, because these are parallel lines cut by a transversal, right? What about the lengths of the segments? Does anybody want to hypothesize something about the lengths of the segments? Length of the mid-segment compared to something? Katie, what do you think?
Like the mid-segment, so DE plus DE equals AC.
Oh, that's interesting. You said the mid-segment plus what?
Plus itself again.
Oh, okay.
As long as the
bottom one. Okay, so another way of saying that is the mid-segment is half as long as the third side. Let's check that one. Okay, so let's measure the length. So that gives us 7.8807 for the mid-segment. And, oops. There we go. And the length of AC is 15.7615. That's a little hard to see, but what if I do something like that? 7.2001 times 2 is 14.4002, isn't it? Yeah, so that's another thing we get. Okay. Was there anything special, any special reason that I chose those two midpoints? I mean, could I have chosen two different midpoints? Right? There's no reason. I mean, I just happened to choose those two, right? And so would you expect there to be any different kind of a relationship if I picked, for example, this midpoint and this midpoint? It'd have to be the same, wouldn't it? There's no, like I say, there's no unique reason I chose those two midpoints, so it must apply to any pair of midpoints, right? Okay, agreed? All right, so we get two important pieces of information out of that. What can we do with that? So how about, come on, let's try this. Okay, so we're told here, what are we given this one? UW, should put a line over that. So segment UW and segment VW are mid-segments of triangle RST. So we're supposed to find the lengths of UW and RT. We're given some stuff. So take a second, look at that. Maybe scratch something. You might want to have a piece of paper out. Get your notebook out maybe. What are those congruence marks telling us? Those congruence marks, in a way, how are they showing us that that's really what this is? We have mid-segments. Yeah, okay, right, because the midpoint, by definition, divides a segment into two congruent pieces, right? Good. Okay. So what do we think here? Anybody want to tell me what the length of UW is going to be? What do you think? Go ahead. 6. How'd you get that?
Because it's half of 12.
Half of 12. Yeah. This segment, because it's formed from the midpoints of RT and ST, it must be parallel. It must be parallel to RS and half the length, right? Good. So that's got to be 6. Good. What else? Jill, can you tell me what the length of RT is going to be? Hang on. Yeah, RT?
16.
Yeah. Right, because you know that VW is the mid-segment parallel to RT, and so it must be half as big as the third side of the triangle. Well, if that's 8, this must be 16. Does that make sense? Okay. All right. Okay, let's go. We don't really need to do that. Let's do that though. I think there's one more thing I wanted to do on here. Oh yeah, this. Suppose you're given only the 3 midpoints of the sides of a triangle. Is it possible to draw the original triangle? What do you think? Think so? Okay, let's try it. To shorten things up here a little bit, we'll cheat and use Sketchpad. But you still, Still have to kind of go through all the steps. Let's say those are the three midpoints. Any ideas? What can we do here? What do you think? Just get us started on this. Let me get us started. What do you think? Yeah.
You connect it into a small triangle.
Okay.
You have the triangle by two to get the.
Okay, it might help to, oops. To connect the dots, create a small triangle. That might be good. So those are the midpoints. Those are the midpoints. So what do we know if, like, FG, for example, is a midsegment, right? Because I'm connecting midpoints. Can anybody tell me the third side that it's parallel to would have to go through what point? It has to go through H, doesn't it? Does everybody see that? Right? And so if I want to, so what I'm going to do here is I'm just going to go ahead and construct a line that's parallel to FG through H. Okay? Okay. What else could I do? Jessica, do you have an idea what else could I do if I want to? I need to find those vertices of the triangle. Kirk, what do you think? Okay, same kind of thing. Let's draw another line that's parallel to FH through G. How about? Okay, good. Now what?
One from that.
Oh, okay, so we'll go parallel. Which one haven't I done? Parallel to.
HG.
Oh, right here, yeah. HG through F. Okay, and let's just. We'll just construct the intersections. Oops, that one wasn't. Okay, construct the intersection, and then this guy. Oops. Oh, I had an extra point in there, didn't I? Yeah, there we go. Okay, good. And then how about if we. I'll just hide all these lines there. There we go, right? Does that make sense? What if we didn't have the benefit of Geometer Sketchpad? It makes it pretty easy. Can somebody tell me a way that I could have, we'll be specific, we don't have to do the whole thing, but can you tell me a way that I could have maybe used my original 3 points to find that endpoint? What's the process I could have gone through? What do you think, Kim?
You could have done the length of FH and added it, well, not really added it, but like put it next to G, and then it would have extended out.
Okay, so one thing I could have done is I could have found the length of that segment, right? And I could have, I know that segment and that segment have to be congruent, right? Okay, but how do I get the directions right there? I mean, because what if that's congruent, but what if I went like in that direction and I would have put the point there? How would I know not to do that? Okay, so it's parallel. So I could use whatever the rise over run is, right, to get from there to there. let's just say hypothetically I rise by 1 and run by 6, then couldn't I go down here and rise by 1 and run by 6? See what I'm saying? Okay. Good. All right. There we go. Okay, I think that's all we really needed to do with that section. Yeah, we can skip all that. Okay, so now that's one thing I wanted to show you. And the other thing I wanted to show you was this. Okay, inequalities in one triangle. So the triangle inequality. So if we want to decide which is the longest or which is the shortest side of an angle or which is the biggest angle or the smallest angle, you've probably learned this, I'm guessing. How much time? Are we almost out of here? 7 minutes. Okay, yeah, then we'll just get through this one more part. So one thing we know is that the largest angle is always opposite the longest side. Another way of thinking about that is the largest angle looks at the largest side and the smallest angle looks at the smallest side. Okay. So can you tell me here, well, because AB equals 3 and BC equals 5, we know that angle A has to be a bigger angle than angle C, right? That's always going to hold. Same is true for angles, right? The converse of that is also true. So we could say, we know that because angle D is greater than, the measure of angle D is greater than the measure of angle E, I know that side EF has to be larger or longer than side DF, okay? So what would be, I mean, if we can arrange the angles in order, I mean, this is pretty trivial. We could order those sides, couldn't we? What's the longest side going to be? Okay, next longest side? GJ, and then the shortest side? HJ, okay. Good. Okay, that's, I mean, I'm not going to spend more time with that. Here's something that pops up that's kind of minor. It makes sense. I want somebody to kind of just, not formally, but just talk us through why this has to be true. The exterior angle inequality. It tells us that the measure of an exterior angle has to be greater than the measure of either of the two remote interior angles or non-adjacent interior angles. Katie, what's one way, how could you say, well, that has to be true? Duh, because
the measure of that angle adds up to the measure of both of those angles.
yeah, okay, because the exterior angle theorem told us that the measure of an exterior angle always equals the sums of the measures of the two remote interior angles, right? And can an angle in a triangle be 0? No. If an interior angle were 0, it's no longer a triangle, right? And so because each of these angles has to have some non-zero, they're both greater than 0, then obviously the measure of angle 1 has to be bigger than either one of those individually, right? Okay, that's true. Okay, so what can you tell me about this then? See how specific you can be. This, I don't know why I guess this is like a director's chair has a seat that's like a triangle when you look from above. So in this triangle, they're telling us that AB is equal to AC and BC is greater than AB. So what can we conclude about the angles in triangle ABC? Maybe it helps. We could maybe add some congruence information here that might help a little bit. Okay, so we know that angles B and C are congruent by the base angle theorem, right? Because if these sides are congruent, those angles are congruent. Now, what does it mean that side BC is greater than AB? Okay, so BC is the longest side. So what's the greatest angle? Okay, A is the greatest angle. Can you maybe put some angle measures on this? Could you tell me something? Could you say, tell me an inequality that would define all the possible values for angle A?
2B 180 minus 2B equals A.
True, okay. But I want an actual number. I want you to tell me that, I'll give you a hint. I want you to say something like angle A is greater than, could be any value greater than this angle measure. No, can't be zero.
It's greater than 0.
It is, but that's not specific enough, yeah.
Greater or equal to 90.
No. So we know that angles B and C are congruent, right? Their measures are equal. I know that measure A has to be bigger. Well, how much bigger does it need to be? 1 degree? Could it even be, could be even less than that, because it could even be greater by 1.5 to 2. Or,
So this has to be greater than 60.
so what's it have to be?
Greater than 60.
Okay, yeah, that's the answer. So we know, now see if everybody can see that. So the measure of angle A, all we know for sure, we can't tell you exactly what it is, but it has to be greater than 60 degrees. Somebody, now that's the right answer. Now somebody else gets to do the heavy lifting here and explain why. Why is that the case? How could you prove that? Yeah.
Because 60 is 1/3 of 180.
Okay. So if all of the angles were congruent, it would be an equilateral triangle, an equiangular, right? And then they'd all be 60. Okay. It's not though. These two angles are congruent, but this one's a little bit bigger, right? Well, how much bigger does it need to be? Well, there's no amount, right? It could be infinitesimally bigger, but it's just got to be a little bit bigger than 60, right? 60 would be the case if it was equilateral or equiangular. So what could you tell me about this, about the measure of, say, angle B? It's got to be less than 60, doesn't it? Now, those two are related. If I told you that the measure of angle A was like 80 degrees, you could tell me what the measure of angle B was. But without knowing anything about the measure of angle A, the only thing I do know is it has to be less than 60, right? You get that? Okay.